Swayam Prabha. Digital India. Educated India.
So welcome to lecture number 47. So we already saw that how the probability for a weak electromagnetic radiation can be written. But this formula, as we say, it is very deceptive because it assumes monochromatic irradiation, okay, and short interaction scales of times. Okay, so these two requirements are obviously inconsistent with one another because of Heisenberg's uncertainty principle. Delta E into delta T has to be greater than or equal to H bar, or delta frequency into delta T has to be greater than or equal to 1 over 2 pi. Okay, this must be always satisfied. This is Heisenberg's uncertainty principle. Okay. So if a monochromatic radiation is really applied to a system, okay, for a time delta t, the system sees the radiation of width. So if monochromatic radiation is applied to the system for a time delta t, okay, then the system, okay, sees the radiation of width delta v, which is equal to 1 over 2 pi delta t in the frequency space. Okay, so in a nanosecond pulse of radiation has an intrinsic width of about 160 megahertz in the frequency space. So before we actually use this equation of the probabilistic equation, if we use this equation, let's put this as 1 so that it is easier for us to do. So before equation 1 can be used, the effects of finite frequency spread okay, of the radiation must be included. Radiation needs to be included. So if we consider the radiation applied to the system to be broadband rather than monochromatic, so let's assume that we have a broadband radiation, okay, and this broadband radiation has a radiation density which is rho epsilon naught e square by 2. Okay, so the total transition probability therefore will be given as P01 equal to 2 mu 10 square by epsilon h bar square omega sine square. It's basically integrated over all the frequencies. Omega, which is therefore P10 is written as 2 mu 10 square epsilon naught h bar square rho v omega 10 integral square omega 0 by 2 square d omega. This ultimately gives rise P10 as mu 10 square divided by epsilon h bar square rho v omega 0. This is this omega rho omega is assumed to be slowly varying, okay, near omega 10, so that it can be removed from integration. Okay. This is indeed the case because sine square, if you look at sine square, this particular term that is marked here, this particular term, okay, is sharply peaked. At omega equal to omega 0. Okay, so therefore the absorption rate per molecule is given by mu10 square epsilon h bar square omega 0. Okay, this is the absorption. It's sharply peaked. In order to derive an expression for the absorption coefficient in terms of the transition dipole moment, this equation, if we call this equation 2, say, this equation, okay, needs to be compared, okay, with the other equation now. Needs to be compared with, remember the old equation that we had, level system, V10, V0 and naught. You recall, so that was the equation that we had earlier. Okay. So, as you can see, so the absorption, in order to derive the absorption coefficient, this equation is now compared with this equation, right? Okay. With the assumption that N naught is almost equal to N for weak field. Okay. So dividing by N basically gives the transition probability per molecule. Okay. So dN1 by N dt is equal to E10 rho V E10. Okay. Or dP10 divided by dt is equal to E10 rho V. This here there is a factor of 3 which is missing in this particular equation, in equation 2, because this has been derived from isotropic radiation traveling in x, y, and z directions, whereas equation 2 that you see over here has been derived using a plane wave traveling in the z direction only, since only the z component of the isotropic radiation is effective in inducing a transition. Okay, so also noting this, and also noting that rho v is equal to 2 pi rho omega, V10 therefore becomes 1 over 6 epsilon h bar square mu 10 square, which is equal to 2 pi square 3 epsilon naught h square mu 1 naught square, and A 1 to 0 is 16 I square gamma cube 3 epsilon naught 8 C cube mu 1 naught square. So these two equations now are the key results because they relate the observed macroscopic transitions to the microscopic transition dipole moment of an atom or a molecule. Okay, so we normally, if we substitute the numbers, A10 will be actually equal to 3.136 into 10 to the power of minus 7 cube mu 1 naught square. This is in centimeter inverse, and mu 1 naught is in dBi. Okay, although these equations are essentially correct, one factor that we have ignored over here is the possibility of relaxation. So these things relax. Collisions or spontaneous radiative lifetime of the upper state has been ignored so far. So we have neglected collisions and spontaneous continuous radiative lifetime upper state. Okay, so when these losses are considered, okay, the molecular absorption line shape, okay, changes from Dirac delta function is delta naught, which is basically infinitely sharp and and infinitely narrow. Okay, so this is the Dirac delta function to a real molecular line shape. So this converts to a real molecular line shape. Okay, so this molecular line shape is called, it's given as G, which can be either a Lorentzian or a Gaussian. Okay, this is of uni but finite width and height. As a result, the equations can be rewritten now. So 2 pi square 3 epsilon naught square mu 1 naught square G is the first one, and then A 1 to 0 gamma 16 I cube gamma cube divided by 3 epsilon naught HC cube mu 1 naught square G B minus B1 naught. So these were the two expressions that you get, in which these are the actual absorption coefficients and the emission coefficients. So, so basically, if you integrate it across all frequencies, you will get just the coefficient B. Okay, so so these are all have dimensions of -1, and this has the dimension of again second inverse, sorry, not -1. So also note that the two levels 1 and 0 are assumed to be non-degenerate. The usual cases of degenerate atomic and molecular levels are a little bit more complicated. So the energy levels are considered to be degenerate. So now that we have taken this detour, now you can understand when we wrote in our Beer's law, right? You recall your Beer's law. We wrote that dn1 by dt, okay, was equal to sigma f n0 minus n1, where sigma was equal to 2 pi mu1 naught square divided by 3c gamma g b minus 1 0. Okay, which was this had the dimension of meter square. Okay, this is the dimension of meter square. The physical interpretation, we also say this is the effective area that the molecule presents to a flux of photons of flux, to a stream of photons of flux x. Okay, so so it is now therefore very convenient, so to say, if we now cast this sigma in this particular form, a square g 8 pi equal to lambda square g 8 pi tau sp. Okay, so which relates to the cross section of the to the radiator. So this is basically linking the cross section, which is basically what is sigma to radiative lifetime tau sp is equal to 1 over a 0 of a transition for a two-level system, of a transition for a two-level system. The subscript sp refers to spontaneous emission. So this is spontaneous emission. Okay. This is the inverse of the lifetime. Okay, so this can be related to real multi-level systems by doing other methodologies. So now let us look at that if a flux, so let us look at if a flux, okay, f is incident on the left of the element thickness dx. This was the thickness dx, if you recall. This was the thickness dx. Okay. That is what we did earlier. The thickness dx on the left with a small element of thickness dx with a cross-sectional area of 1 meter square. Then the change in flux, caused by passing through the element, is given as df equal to minus sigma f m naught minus n dx. So upon integrating over the absorption path, okay, this becomes, if it was f naught to f by f minus n1 0 to l dx, okay, or ln f naught is equal to ln or I naught is equal to minus sigma n naught minus n1 to L. Okay. Or in other words, it can be written as I I is equal to I dot exponential minus sigma n naught minus n1 to L, which is called the Beer's law. Actually, it is written in a slightly different form in several textbooks. So here sigma, of course, is reported in centimeter square. Okay, n is in molecules per cc, centimeter cube, and L is in centimeter rather than the corresponding SI units. Okay, so if we consider alpha is equal to sigma n naught minus n1, therefore I will be written as I naught e to the power of minus alpha L. L. Okay, so this will be the expression. Okay, so this sets the stage now that we have seen. This is what Beer-Lambert's law is. Now, for a spectrum of a real molecule, we need to know the line shape functions, right? We need to know the line shape functions. So Beer-Lambert law, as you can see, it serves different purpose. It allows you to calculate the concentration, okay, so long as you know what this guy is all about. Okay, and you know the length. So as you can see, it is dependent on the length. So more the length, more is the sensitivity of this particular parameter. So it is easy to measure experimentally. Okay, so but in real life, we still need to know the real spectrum. Okay, of a molecule. So the line shape functions basically falls into one or two of the general categories. One is homogeneous, and the other one is inhomogeneous. Well, that did not require much of a guessing. The homogeneous line shape occurs when all molecules have identical line shape functions. For example, if an atomic or molecular absorber in the gas phase is subjected to high pressure, then all molecules in the system are found to have an identical pressure broadened line shape for a particular transition. Pressure broadening of a transition is therefore said to be homogeneous broadening. If this is one example, is therefore pressure broadening. We'll see more of these a little later. On the other hand, if the molecule is dissolved in a liquid, and then the disorder inherent in the structure of the liquid provides different, environments. Okay, so the absorption spectrum is made up of different spectra of different molecular environments. So this is therefore called inhomogeneously broadened. Okay, so let us look at natural lifetime broadening. So what is natural lifetime broadening? Consider once again a two-level system, okay, with an intrinsic lifetime of about tau sp. Okay, this is E1, this is E0. Okay, so this is the 1, 0 is 1 over tau sp. Okay, describes the state of the two-level system in the absence of electromagnetic. So let us, once you do that, the wave function that describes the state of the system is given as psi t. Go to A0. This is also, we have done it before. Again, do it here. Bring it here. Okay, so this is now given as, writing it in terms of the time independent portion of the wave function. H1, where these are simply constants. Okay, should the system be excited into a superposition state? Okay, the dipole moment of the system is therefore given by this is once again the time dependent portion, and which is equal to 1 0 a0 star a1 omega naught t plus a naught a1 star bi omega 1. Okay, so that's the real part. 2 1 0 a0 a1 star 0 2. Okay, so this is your empty. Okay, assuming space fixed moments both vanish. Okay, so the dipole moment of the system oscillates at the Bohr angular frequency. Okay, the dipole moment of the system oscillates at Bohr angular frequency, the one not as empty is equal to 2 a naught a1 mu 1 naught cos omega 1. So these are chosen to be real numbers. Real numbers. Okay. Okay. Now, if the population in the excited state decreases slowly in time relative to the reciprocal due to spontaneous emission, then the amplitude of the oscillation will also decrease. This corresponds to a slow decrease in A1, okay, at a rate of gamma by 2, where gamma is 1 over the relaxation time for the spontaneous emission, which is nothing but A. So in other words, we can write the oscillating dipole moment now. Moment now is nt equal to m naught minus gamma by 2 omega 1 0 into t, where this is nothing but 1 over tau sp is equal to a1 0. Okay, so it corresponds to a slow decrease in A1 at a rate by 2. Okay, so this is what the dipole moment now looks like. Okay, so it just kind of tries to, it is an envelope along which it kind of goes down. So it is something like this. This slowly coming down. So this is basically envelope, which is E minus gamma t by 2. This is N, and this is time. This is how the dipole moment actually comes down. Okay. Okay, so in the next class, we will see how this dipole, what are the different line shapes that are possible, like the Lorentzian and the Gaussian that we already mentioned, and how they depend on this dipole moment, or transition dipole moment. Thank you.